Good afternoon. Thank you all for having me. My name is Ian Haken. I'm a security software engineer at Netflix. And I've spent about 6.5 years there, mostly working on the platform and infrastructure security team. And today I want to talk about some adventures in authentication and authorization. And to kick it off, I want to talk about one of the first times I got admin credentials to our cloud ecosystem. So this was during a red team exercise. It wasn't just while I was walking down the hallway. So I was acting as a malicious insider, and the target of my attack was this key service we have running in our cloud environment. The idea behind this key service is that it sort of hands out different flavors of credentials to developers, like building code at their desk that's later going to run in the cloud. But the thing that makes the attack interesting is that it's not something I can talk to directly. It lives up there in our cloud, in our VPC, something with firewalls around it, all those good things. So the way you actually interact with this system is through our Internet Gateway service. So this is the thing that I actually log into with my SSO credentials, and that's going to proxy the request on my behalf up to this key service. And the key service is going to turn around and say, OK, well, is Ian actually allowed to get the key he's asking for? So it's going to call out to our authorization service. That's going to give a yes/no answer. And this is sort of all fine, the way I've drawn it. The challenge with this diagram is that there's a hop between the thing that I logged into and the thing that needs to know who I am in order to do that check that I'm allowed to get the key. So the way this was initially solved during the course of this exercise is the Internet Gateway throws in this little header, says who is the user, and passes that up to the key service. And that's a little bit problematic for probably a handful of reasons. But the big problem is that anything else that's sort of in this ecosystem can put whatever they want to in that header. So if I get control over something else that's able to talk directly to the key service, then I can pretend to be anyone. And fortunately for me, pretending to be an attacker here, there's a convenient service already running in the environment that lets you run whatever code you want. We've got this Python notebook system, lets you run data, run queries against our big data warehouse, schedule those things to run later. But importantly, it literally lets me run whatever code I want. So I was able to ask it to go talk to this key service, put admin in a header, and give me some credentials back. So that's the picture that I kind of want to talk about for roughly the next 20 minutes. And talk about the various iterations we went through trying to make improvements to this ecosystem. And importantly, talk about a lot of the things that didn't quite work, that still had problems, had different threat models we hadn't considered. And if you're working in a similar space, thinking about problems like this, or really just trying to solve authentication and authorization in your ecosystem, I'm hoping to just save you some time and kind of fast forward to this last step that we were finally happy with. So all right, talking about authentication and authorization. And so before I get too far into it, I'm just going to spend 1 minute to define those terms, make sure we're all talking about the same thing. So authentication, aka auth-n, is establishing your identity. Usually there's some form of credential involved. There's a bunch of different ways you can do authentication, a lot of different technologies. But at the end of the day, it's proving who you are to the remote system. And then authorization is the other piece of it. Once we've established who you are, we want to know, are you allowed to do the thing? So the thing can vary a lot depending on the context. Usually there's some resource you're acting on, some type of action. You might be doing a read versus a write. There can be a lot of other dynamic factors pulled in, what sort of roles you have, whether you did MFA when you logged in, what IP you're coming from. Lots of things can feed into that. But authorization output is basically a yes or no answer. And one of the things that we've been seeing a kind of industry trend for is a sort of centralization of a reusable, optimized authorization system. And that's kind of what I'm alluding to with this picture over here, where my key service is calling out to something. It's calling to something that has rich, expressible policy language, a lot of information about roles and attributes on the user. And there's some links here that you can look up with some examples of some of these sort of optimized authorization services. But going back to our picture, the first fix that we wanted to lean into is using forwardable bearer credentials. And so bearer credentials are basically just something that proves who you are that can be passed along kind of regardless of the context of the specific request. And this is a great blog post I really like that does a really good survey. It truly is tedious. It goes through a lot of different technologies. But regardless of the specifics of that, the relevant bit here is that it's something that can be passed along the hop. So I do my SSO login here, I authenticate, I get some kind of like OIDC access token or JOT or Presedo or Macaroon or Biscuit, whichever is your favorite. And that can be passed along when my internet gateway makes a call to the key service. So the key service is able to validate that this is actually an authentic credential, unpack the username from it, make the same authorization check as before, and now this sort of solves the initial problem. If there's some sort of remote code execution in the service, it can't pretend to be anyone. It has to use a real credential that can be verified by the key service. So this resolved the initial problem we had. But we ran into a different problem with this picture. And the different problem here is because of a completely different service. So in this case, we had a travel service. This was an off-the-shelf piece of software that does sort of hotel and travel bookings for us. And this was part of the same ecosystem. So my bearer credentials were passed in there whenever I went to go book a flight with our internal booking system. But the problem is we had a really good vulnerability scanner set up, discovered that there was an unauthenticated RCE in this service. And it turns out it was because it was pulling in some super old version of open source library, had RCE in it. Lots of good red teams that I work with. And the question came up during the incident review, what's the worst case scenario if a malicious actor had gotten into the system? Well, they have to have real credentials in order to make use of these calls to other systems. But the problem is that this is a service that was used by basically every employee at the company. So when Joe Admin went and booked his flight, his credentials flowed into that service. And those credentials could have been forwarded by a malicious actor back up to this key service. So this is another way of getting admin credentials from a single point of compromise, completely unrelated to the security of that system. So sort of the lesson in walking through that incident review is that using bearer credentials specifically in this way introduces a high risk of compromise from any single point of failure. Because any individual service in the whole ecosystem that gets compromised, any user that has gone to it can now have their credentials harvested and reused in this way. So one potential fix for that that people have asked me about a lot is, what about using credential scopes? So credential scopes is a bit of an overloaded term. It can kind of be implemented a few different ways depending on exactly which authentication technology we're talking about. So like JOTs have an audience in them. OIDC tokens have scopes. But the idea is that your credential, instead of just being the same credential you use everywhere, has something embedded in it that says what it's meant to be used for. So when I go to the key service, I use one flavor of credential or something with my username in it that says this is for getting keys out of the key service. And when I go and talk to that travel service, I have a different flavor of credential, a different audience or scope embedded in it that says this is usable for the travel service. So this solves the problem somewhat, because then these credentials I'm sending down there can't be replayed against the key service. But the problem is that this only works in sort of a static, unchanging microservice ecosystem. So one enhancement that came along down the road is that the calendaring service wanted to get users' calendar data. Sorry, the travel service wanted to get users' calendar data in order to find like empty blocks in your calendar, go book flights during that period. But those credentials that we're sending down to the travel service can't be used against the calendaring service because they don't have the appropriate scope. Instead, the credentials that get sent down have to have scopes for both services in them. But you can't just magically change the scopes down here. That would sort of defeat the whole point. Instead, that has to be configuration that's propagated all the way back up this call chain. The travel service needs to use multi-scope credentials. And so your initial authentication needs to embed both scopes in it. And that kind of cascade maybe isn't that big of a problem in the picture that I've drawn. But Netflix is a really big microservice ecosystem. We have literally thousands of microservice applications. And any given API call, based on some traces I pulled up preparing this talk, has on average around 10 different microservices it ends up talking to. So when you look at a given API call, having any idea about exactly what scopes you would need to embed to include all of those different microservices it talks to is really hard to figure out just a priori. And even if you do a really good job of that, you get a snapshot of your ecosystem, find out everything that every call is going to talk to, you have the same problem I just mentioned before, where as soon as a new dependency gets added, that has a cascading effect where whatever configuration enumerates the scopes that are needed has to go back up every single microservice and ultimately affects dozens, if not hundreds, of engineers. So in trying to think through how we would roll this out, our takeaway was that using finely grained scopes like this, at least in the context of like trying to map them to a single microservice and keeping up with that, was just intractable at a system as sort of agile and dynamic as the one we were working in. So we basically gave up on that effort. Instead, what we did was lean into service-as-service or S2S access control. So the idea here is that in addition to the user having credentials, each individual microservice has its own credentials that it uses whenever it talks to the next hop in the chain. So in this case, our internet gateway is going to authenticate down to this compromised travel service. The travel service has to authenticate up to the key service. And importantly, on each hop along the way, there's an access check. And here the key service would check, is the travel service allowed to talk to the key service? And the answer should be no. There's no reason that should be talking to me. So that blocks this particular attack where a user's credentials can be replayed against that. So I think this is what, at least in my experience, people mean when they talk about sort of zero trust microservice design, where every hop along the way, you don't take for granted that that service should be talking to you. You want to know who they are and are they in some kind of access control list. So in rolling this out, we kind of ran into a couple of gotchas that are worth pointing out. The first is just, I mentioned that each service should authenticate to the next hop, but exactly how do you do that? If you're using the same type of authentication technology as I said we should be using for users so that it can be passed along, then you basically end up eroding everything you're trying to build. Because in this case, the internet gateway authenticates down to the travel service, and that service could just harvest that credential, replay it against the key service, and now you've kind of gained nothing in this whole design. So the lesson there is that whatever authentication technology you use, it needs to be something non-forwardable, in contrast to what we've been talking about for the user credentials. And exactly how you do that, you kind of got a lot of choices. You can either use finely scoped bearer credentials or MTLS certificates. That's what we ended up leaning into. But the point is it should be something that you can't just sort of verbatim replay. And the other pitfall sort of alludes back to that previous slide, the fact that we've got this really big ecosystem with really deep call graphs. And in each step of that call, I'm now suggesting that we add an authorization check where we say, is hop n-1 allowed to call hop n? And that means that for any given API request, we're going to end up having about 10 authorization checks. And if you're doing an RPC to some centralized authorization service, then that's adding 10 times 1, 2 milliseconds. And that adds up. That's like 20 milliseconds for every API call. And if you've got a very rich homepage that does dozens of API calls just to load it, you're just adding up to now hundreds of milliseconds, which is just a non-starter for basically everyone we talk to about this. So the way you implement this is really important. And the thing that we learned in talking to our partners is that we really have to come up with a solution where the authentication and authorization can be performed locally. So there's an old talk we gave. You can look that up later. That's still very relevant. That really goes into the details of how we built in this authorization story to be zero round trip. And it's basically just pushing down ACLs and evaluating those locally. But you really want to design that into how you actually implement these features. So, all right, that's S2S. And that does block the last attack I was talking about, because now our compromised service can no longer go and talk to the key service. But there is one more attack in this picture that, in hindsight, was kind of obvious, but actually sort of took us to this level of iteration to really consider and defend against, which is we've got our credentials being harvested by this compromised service, and it can't go talk to the key service directly. But there's nothing stopping it from just replaying that credential back against our front door, back against the internet gateway, because that sort of looks just like a genuine user, and that can be played directly against the key service. So whether this compromised service is exfiltrating these credentials or actually literally calling the internet gateway itself, the fact that we've forwarded the actual user credentials along every call inside our ecosystem now means we actually still have the same problem as before. Any individually compromised service can have those credentials exfiltrated and reused. So the lesson there is that we don't actually want to forward the actual end user credentials internally, because that has the same problem as before. Any single point of compromise leads to badness. So our fix for that was to use something that I'll call end-user context ticket. So I lifted that term from Google's Beyond Prod white paper. We actually developed this technology independently, called it something different, but we don't have a public write-up about it, so I'll use that term. And the idea is fairly straightforward. You still forward the end-user credential off to this ticketing system, but what that does is verify these credentials, bundle them into a new form of credential called an end-user context ticket, has the same data inside it, but it's a different form of bearer credential that's meant to be forwarded around internally. So that ticket is what gets passed around instead of the actual user credentials. And now if there's a compromised service that gets a hold of that ticket, well, it's sort of useless. It can't be passed back to the front door because that only accepts the actual user credentials. And because of our implementation of S2S access controls, the compromised service can't talk to the key service directly, even though it has a good ticket, but the service-to-service access control prevents that. So this is sort of the final picture of the state that we ended up being pretty happy with, that sort of blocked all these different styles of attacks and compromise that we were worried about. But this has a different problem, and it's no longer really a technical one. Instead, it's a human one. Everything I've just described now has several different flavors of authentication technologies, has several different ways of doing Auth0, and it's a lot to wrap your head around. So we've got not just different types of authentication technologies, we've actually got different flavors of bearer tokens. We've got MTLS certificates in the mix. We've got multiple authorization tools, one for doing the local S2S access control, one that has a centralized, robust policy engine. And in practice, we've actually got several flavors of remote policy services that have been sort of optimized for different verticals and use cases, and reverse indexing and all sorts of things. And to operate in this system, to actually sort of be secure, you have to be able to use all those technologies. Otherwise, there's not really a good way for this authenticated RPC call to reach you. So how do we allow our developers to operate in this ecosystem when we have all these requirements for what they have to do? And the answer to that is probably not too surprising. It's the answer to everything in computer science. It's add a layer of abstraction. But how we did that, I think, is sort of just useful to illustrate. So we've got all these different flavors of authentication. We've got the bearer tokens when you come into the internet gateway. We've got MTLS for the service-to-service authentication. We've got these end-user context tickets. But regardless of how a request comes in, regardless of which combination of things get used for any particular hop in this call graph, our platform packages this all up and creates an authorizable context. And this is just an opaque object that our developers are able to work with. And basically, the only thing you can do with this totally opaque object is to pass it into our other abstraction piece, which is the authorization client. And this is a thing which is configured under the hood to go talk to whichever flavor of authorization makes sense for the application being developed. So when a developer actually wants to write some code, like this key service, where they're implementing this RPC now, they can inject this authorizable context, which is some kind of opaque thing that they can just take for granted will be there through magic in any given request. They can wire up whichever authorization client they want configured, and you just pass that authorization context directly into it, and it's going to give you a yes/no answer. And as part of a platform provider, we also give you other useful utilities, like being able to log that authorization context, a bunch of things that know how to unpack it under the hood so that our developers don't need to try and introspect this thing, because that's sort of the abstraction barrier we want to keep. So that's basically everything I wanted to talk about today, but I think there's sort of three takeaways that really sort of summarize everything I just said. And the first is really what I've been talking about since that very first slide, which is that you want your end user identity propagated throughout your ecosystem in order to actually have useful fine-grained authorization at the back of your call graph. And so if you're going to do that, you need to actually have verifiable and forwardable identity. Otherwise, you have that problem that we had on the first slide where anyone can pretend to be anyone. But you want to avoid passing the actual user credentials in order to solve that. And that's what the end user context tickets are for. Service-to-service authent and Auth0, on the other hand, that limits any single point of compromise. Again, that's sort of zero trust. That's why everyone's been talking about it for the last however many years. But that needs to use a different technology. It shouldn't be something forwardable, because that sort of erodes everything you're trying to build with that. And there's some unique requirements, in particular for our use case at our scale, that says we can't use the same centralized authorization service that we want to use for other use cases. And so the last takeaway is just, if you believe these first 2 points, then you're not going to use a single Auth-N or Auth-Z technology in your ecosystem. And so you really want to plan accordingly as you go out on this journey. And for us, that meant be nice to our developers, provide a good layer of abstraction, means they don't have to think about these problems. But the nice thing about abstractions is that they're useful for you too, because it allows you to be agile in exactly which bits and pieces of Auth-N technology you pull in. Because if you're anything like me, it's going to take you more than one try to get this right. You're going to try some new Auth-N and Auth-Z technologies, and that abstraction layer kind of defends you against having to tell your developers to update their code yet again. So that's it. Thank you all for coming, and I think we've got about 7 minutes for questions.